in this video, we're going to look at functions that are defined piecewise. So we already have one example of a piecewise type function, and that's absolute value, because an absolute value function has different equations in different parts of its domain. But we can also define these piece by piece, and so that's what we have here. So let's say we have the function, we can see here these three equations for different parts of the domain. If I look at the whole domain, I see that overall this function is defined for all real numbers, because I have a section for values less than -5, a section for values between -5 and 2, including those two values, and a section for values that are greater than 2. So together they cover the whole number line. So x can be any real number. So I'm going to look at them piece by piece. My boundary lines are at -5, so I have one explanation for there. -5 to 2, so we have a different equation for this interval in the middle, and x is greater than 2. So starting with -5. Now, if x equals -5, I do not use that first equation. But since I'm looking at that first piece of the function, I do actually need to consider what would it be if I plugged in -5. So -5 minus 2 is +5 minus 2, which is 3. So I'm going to use an open circle here at the point -5, 3, because that isn't actually how I would calculate this function. But now that line is a line with a slope of -1. So I can either plug in certain values, or I can just use what I know of linear functions. So for example, I could say -6 minus 2 is 4, -7 minus 2 is 5, and so on. But I know this is a line that has a slope of -1, so I can just sketch it. So that's the first piece of this function. The next piece of this function is, again, a line. It's linear. So if I plug in -5, and in this case, I'm going to use a solid circle because x can be equal to -5 in this interval. So -5 times 2 is -10, plus 13 is 3. Oh, that actually is the same point. So I can see that these connect, and now I can fill in that circle. I'm also going to use the other boundary point, 2. So 2 times 2 plus 13 is 17. So when x equals 2, y equals 17. And again, I use a solid point here because the 2 is included in that interval. Now, I'm going to put in a couple more points in the middle here. For example, that y-intercept is 13. I know the slope is 2. So for every 2 I go up, I go over 1. So I'm going to fill these in a little bit just to make sure that the slope matches. And then I connect everything in that interval. And that is the second piece of my function. The third piece is for when x is greater than 2. And here I have a quadratic, so I'm going to have a curved shape here. Again, even though if x equaled 2, I wouldn't plug it in this interval, I have to figure out where my function is going to go, where the endpoint is basically. So if I plugged 2 in here, 2 squared plus 8 is 12. So I'm going to put an open circle at 2, 12. Notice in this interval, they do not connect. If I plug in x equals 3, 3 squared plus 8 is 17. So I've got a point here. And this is part of a parabola curve. If I think about what the rest of this parabola would look like, its vertex would be at 0, 8. So it'd be here-ish. I would have a parabola looking like that. But what I've drawn in red is not actually part of the function. That just helps me get the shape right. What is drawn in blue is the function, and I can see that it exists in 3 pieces. Now, at the boundary points, one of 2 things could happen. At -5, we have a function that is continuous because it connects. The 2 pieces join each other, and I don't have a gap. Whereas at the 2, I have a function that is discontinuous because there is a jump. Again, you've seen discontinuities. You've seen them with rational functions in both point discontinuities and asymptotes. You've seen gaps in your graph, and that's just what happens here in this piecewise graph.